Most ions that are incident on the sample penetrate the sample without being scattered. This is because the incident ions must collide with the sample nucleus to scatter. However, the interaction range owing to the electric force between the sample nucleus and the helium-ion nucleus is very short, therefore, collisions rarely occur. However, a considerably small number of incident ions collide with the nuclei present in the sample with a very low probability, resulting in scattering and significant energy loss. In addition, because of the very low probability of collision, the sample destruction is very small. Therefore, this can be classified as a non-destructive analysis method. The ratio of the energy scattered by the elastic collision between the incident particle and the nucleus of the sample can be expressed by the following equation. This is known as the kinematic factor and is determined by the mass fraction of the nuclei colliding with the incident particle and the scattering angle. After measuring the energy of the scattering particles by placing the detector at a well-defined scattering angle position and analyzing it using the kinematic factor value, the elements of the sample can be determined. This will enable to determine various elements within the sample. For example, in a sample comprising 3 elements, ions are scattered by each element, resulting in different energies, and each spectrum appears at a different position in the energy spectrum. Most ions that are incident on the sample pass through without scattering. However, even if they did not collide, they pass through the medium with very weak electromagnetic interactions. Owing to these interactions, the incident ions lose energy and gradually become slower. The incident ions slow down in proportion to the number of atoms in the sample passed. This is called the stopping power. Because of the energy loss owing to weak interactions, the incident particles lose energy with a statistical deviation. This is called straggling. Stopping power and straggling vary depending on the elements of the samples, and are well known through various theories and databases. Therefore, by measuring the energy lost as the ion beam passes through the sample, the thickness of the thin film can be calculated based on the density and stopping power of the material. Let us observe how the scattering energy is determined when the incident particles scatter backward by considering the kinematic factor, stopping power, and straggling. When the incident particles collide with the nucleus in the surface atomic layer of the sample, the energy of the scattered particles is reduced by the kinematic factor ratio. The energy of the particles scattered from the deep layer rather than from the first atomic layer of the sample includes energy reduction by stopping power and energy dispersion by straggling. The figure simplifies the previous explanation. Particles scattered from the surface layer of the sample are green, those from the middle layer are red, and those from the deep layer are blue. If the same element is thickly distributed in the depth direction of the sample, the width of the spectrum increases, as indicated by the dotted line. These spectra are examples of the sample containing gold, silicon, and carbon discussed earlier. When the sample is thin, the spectrum becomes narrow, as shown by the solid line spectrum, and when the thickness of the sample increases, the spectrum becomes wider, as shown by the dotted line spectrum. Although elements of the same number exist in the sample, the larger the atomic number, the stronger is the repulsion of the incident particle, generating more scattering. Rutherford derived an equation expressing the probability of collision detection between the ion and the nucleus of the sample in a specific direction. This is called a differential scattering cross-section. This value increases as the atomic number of the target nucleus increases. incident energy decreases, and scattering angle decreases. Therefore, if the number of incident and scattering particles is precisely measured and the scattering cross-section information of each element is used, a quantitative analysis of each element can be performed. The number of scattered particles can be expressed with the following equation. The number of scattered particles is proportional to the scattering cross-section, solid angle of the detector, number of incident ions, and areal density of target elements in the sample. By measuring the number of scattered particles, the quantitative number of target elements in a unit area of a sample can be analyzed. Let's assume that the MEIS spectrum of a thin hafnium oxide film of 5 nanometers measured under specified conditions is the same as the black solid line spectrum. If the number of incident ions is doubled, the height of the spectrum is doubled. When the hafnium concentration is reduced from 33.3% to 16.65% while maintaining the same incident ion number, the height of the hafnium spectrum is reduced by half. When the thickness of a sample increases from 5 nanometers to 10 nanometers while maintaining the same composition, the hafnium spectrum doubles in width while maintaining its height. In conclusion, MEIS measurements can be used to perform quantitative analysis without a reference measurement.